Hi, everyone. Welcome to the talk about building infrastructure for machine learning applications. My name is Natalie Pistunovich. I am on Twitter. My handle is Natalie Pis. And the Twitter handle of this meetup is Golang WAW. And the hashtag, if you speak about anything Go related, is Golang. So you can use that, and there's a bot that would randomly retweet stuff with this hashtag. Always nice. A couple of years ago, I helped a friend of mine in an online challenge that he was doing for a conference. So it was kind of a sidetrack in the sense that this takes place in parallel to talks, and this is basically an adventure game or kind of a CTF where you have to break all kinds of challenges, and then you get a hint or the key or the tool that helps you with the next one. And the help that I was doing is basically validate that you can break into such a screen within a reasonable time of 2-3 hours. And the hint or the thing that you received from the previous level was the machine learning model that was upon which the CAPTCHA in the screen was trained. And you basically need to build something to do this. And I said, hey, that's a great chance to use Go, because who is using Go for machine learning, right? And the way that I did this is the following steps. So first of all, you inspect the model. That means look what are the inputs, the outputs, how many of them, format, and so on. Then load it into the code, and then write the Go code around it, which is try to brute force, basically all the combinations from 0000 to 0001 and 9999. And so for each connection, you open the cookie jar, you get the CAPTCHA image, you make a prediction using that model, and with a combination of the current pin, you try to log in. So with the two parameters of the current pin from the brute force and whatever the machine learning model translated. Machine learning model was pretty good, and it didn't fail often, but for the few times that it did make wrong prediction, as we humans sometimes do, you still have the cookie jar open, so you can just make another iteration and you're good. If there was something wrong, you just move on to the next pin, and eventually you brute force, and this worked out. I wrote about this at the Gophers Academy blog back in 2017 and put all the code to this Git repo if you want to look at it. If you want to take the code and try to reproduce it and so on. Don't use the current version of TensorFlow, because the current version of TensorFlow breaks the Go API. There is a PR that is going to fix this. It has been open since March. If you're interested in this, go to GitHub and give a thumb up to the request to merge this. Everybody's having a hard time, including especially people who maintain all kinds of tools like TensorFlow. So it happens, it's normal, but just make sure you use an older version of TensorFlow if you actually want to run this. But I am not a machine learning person, and this was actually the first time I ever tried anything with machine learning. I use Go. I studied computer engineering. I was hoping to work for NVIDIA. I really loved hardware. The language that I used to write my graduation project in university was CUDA. And then I moved to Berlin, and Berlin is not a city of hardware at all. So I ended up doing Go and started doing that in 2014, I want to say. And somehow with this knowledge of a little bit hardware and some Go, I managed to do cool machine learning stuff. And that's what I'm here to talk about. Last year, I gave some talks on the topics of how to use Go for systems. So actually not for backend, but for the infrastructure part, or for building tools, or for building everything that supports the code. And this talk is kind of like a connection of all of those together. So it brings infrastructure, it brings machine learning, still everything is in Go, lots of tools and some data science. And what I hope is that by the end of this talk, you'll be like, wow, this is so curious, and I have just enough knowledge to be able to go home and start understanding what I don't know. And I hope that there is a good mix of skills in the crowd, because we will need a lot of, yeah, that makes sense, in order for all different pieces to kind of combine and work together. And this gopher I made of myself at the website goforize.me. Really cute to have an avatar, a Go avatar of yourself. So if you want, it's goforize.me. If I'll remember, I'll write a link in the Zoom chat. If not, remind me and I will. And if you see anything cool, please tag the meetup, please tag me, and please use the hashtag of Golang. It's always fun to spread knowledge and share with friends. So what is machine learning? The definition from Wikipedia is the scientific study of algorithms and statistical model that computer systems use to perform specific tasks without using explicit instructions. Basically, it's a variation or a subset of artificial intelligence. What is artificial intelligence? I found this great picture on Twitter that explains what many things of artificial intelligence are. And it includes machine learning, it also includes NLP, it includes automation, robots, supervised learning, unsupervised learning, speech recognition, text recognition, and so many other things. And you can say that artificial intelligence is the intelligence that machines demonstrate, unlike the natural intelligence that humans demonstrate. And the term is used to describe machines that mimic cognitive behaviors, such as learning and problem solving. And another interesting fun fact, artificial intelligence many times thinks of robots, and robots actually come from, I forgot the language, but an Eastern European language, because it comes from the word rabota, work. So it's all about doing things with machines. So how to ML? Those are the steps. First, you define the problem. Are you trying to recognize text? Are you trying to recognize speech? Are you trying to recognize an image? Are you trying to solve some efficiency problem? And you also define what is success. It can be a response within 100 milliseconds. It can be a response that is 99.95% accurate. It can be many things, and it depends on your domain. If you do something medical, you can wait a little on the account of getting something super accurate. If you're doing a recommendation for a purchase engine like Amazon or something like that, you probably want it faster, more than you want it 99 or 95% accurate. And then you gather data, which has to be relevant to the task. So if we're doing English characters recognition, we probably don't want to include Polish characters. And then we prepare the data. So we clean and we pre-process it, and we randomize it. For example, if we're doing digit recognition, the input should not always be ordered 0, 1, 2, 3, 4, 5, 6. Otherwise, the machine will know that if you enter 5, then the next one is 6. And then you do the split to train data and test data. Roughly 75% of your data you're going to use for the training and 25% for the testing. Then you choose a model. This is really hard. It depends on many things. For example, what is the learning task? Is it recognition? Is it prediction? Is it recommendation? And so on. It depends on the input type, and it depends on the number of possible categories, which is basically a number of predictions. So let's say you're doing text recognition, you have 20 to 30 categories. You're doing digit recognition, you have 10 categories. Face recognition, thousands, millions. Hot dog, not hot dog, you have 2 categories. And then you take the model and you train it. You do this by assigning random values and then taking the 75% of the data that you have, the trained data, and you run it through that, and you adjust the weights every time for each step. And if this reminds you something, yes, this is the way you solve partial differential equations. You make a guess and you make iterations until the solution is good enough. And then you take the 25% remaining data and you evaluate your model actually to see how it performs. Many times from here, you will fall back either to step 4 or to step 5. It depends on what went wrong, but you either have to retrain your model or just choose a completely different one. And this is a lot of what data scientists do. And I do think that sometime in the future, in many years, it will be more efficient, but it's a new field, so it's always lots of things to learn about. But if you have succeeded, then you're moving to the next step, which is fine-tune the hyperparameters. So this is done manually, unlike stage 5, where you do this automatically. And then you're ready to good to go. You're going to predict. In case you recognize the logo in my previous slides, TensorFlow is a tool that I really love using for this purpose. TensorFlow is an open source software, even end-to-end platform for machine intelligence that is used for all kinds of applications of machine learning, for example, neural network. And the reason that it's called TensorFlow is that because you have the data represented as a tensor. Tensor is a generalization of a vector or of matrices to higher dimensions. So you describe this with two properties, the data type and the shape. The shape is number of values per parameters and number of parameters. And you take, so this image is a representation of a tensor, of a physical tensor, so from physics, not of a mathematical tensor. And you take your tensor and it flows through the graph. The graph is the representation of the model, so the machine learning model. This is roughly how it looks. And it's made of a set of nodes. Each node is described by a mathematical operation. And basically the data, or the tensor, every step goes through this mathematical manipulation. And you can inspect the value intermediately, so at any node, and you also have the output. This is why it's called TensorFlow. Summarize, we take the data represented with tensors, and it flows through the graph, which is mathematically represented, or the math behind it is represented with a graph. What I like about TensorFlow is that it's community-driven, and it's becoming more and more friendly for developers, and there's all kinds of tools to support that. For example, there's AutoML, which kind of lands you after the stage. You basically drag and drop images and or files and their prediction, and this does the entire chain of commands for you. There is also a huge library called the TensorFlow Hub, which is kind of like a repo for modules, for models. So all the models out there, somebody finished his PhD thesis and built this awesome model and wants to share it with the world, they would put this on TensorFlow Hub. And you can search for models there by all kinds of criteria. For example, if it's text recognition, if it's digits, and so on, and many other filters. And of course, so this would land you to the step where you'll have to train the model, but you have chosen the model. And there's all kinds of tools that are built on top of TensorFlow, which you can also use. But then there's infrastructure, right? We said we're talking about this today. This is a great article written in 2015 by a group of Googlers that discuss the problems in basically hacking up quickly infrastructure for machine learning applications. And I cannot recommend enough to read this. Just take a picture of the name, find it, it's open. You don't have to pay or be connected to some university network to be able to read this. And a lot of learnings and a lot of mistakes and a lot of things they worry about, and a lot of things to take in consideration when you build a model. When you build the infrastructure for a machine learning model, the TLDR is there are infrastructure, let's say that infrastructure for regular applications like web and tools is complicated, but for machine learning, it adds a second layer of complexity. So just be really careful and be aware that you will be making mistakes because it's new. There is a lot more to machine learning than just implementing the algorithm that we covered. Machine learning code at the heart of a real-world production system has about 5% of code that is actually the model. The rest is the system around it. We will now cover different parts of it. So take a deep breath. We're doing a little bit of a switch. I will use the chance to say that as an engineer, I love giving hands-on tips. So I will be naming specific tools. I'll be trying to name mostly open source tools. And I'm definitely naming tools that all have Go libraries or even written in Go. So your entire infrastructure can be made in Go. And it's going to be a lot. So deep breath, here we go. First one is Hadoop, which is part of the Apache Foundation. So let's use the right logo. And it's basically a frame that has several tools together. And it's probably the most, one of the oldest and one of the most common ones. And the nice thing is that you can take whatever tools you need from this group of tools or set of tools to build your own system. And it is being told, but not official, not that I found, that about half of the Fortune 500 companies have some kind of a Hadoop tool in their machine learning or data processing, big data infrastructures. So first of all, there is the distributed file system. There is a MapReduce, which is basically the kind of the entire algorithm that happens. So you have a huge data set and give me the subset of all the people who are over 30 and also from outside of Poland. This is kind of reduced your data set to the specific sample that you need. Then there is the Hadoop common. There is the Yarn, which is slightly less used. And all that makes the Hadoop together all open source. And this slide that we're going into is probably one of the trickiest one in this entire presentation. So I want to give a heads up or full disclosure that I'm going to be comparing apples to pears, or even to papples. And it's a little bit of a mix of types and structures of databases or file systems, if you will, or data types. So take the next slide with this awareness. And so data lake, for those who are familiar with the term, you probably know, you get the context. For those who don't get the context, it's basically a way to represent a lot of data in very different structures. So it can be binary, and it can be data with one schema, data with another schema, and different formats, not just text data, and in an unhierarchical way, but everything is in the original format. And this is basically all the data that you have. It's easy to find each data that you have there, but to use it, you have to go through the APIs or change it and so on. So it has some usage, and it's a common part, let's say, of an infrastructure of machine learning applications. And here are some tools that you can use to build a data lake. Google BigQuery, Apache Hadoop, which we covered, the Apache Spark, the Azure Data Lake, and many others. And again, I want to remind that if you put this slide on Twitter, people will argue, and that's fine. There's more than one definition. And this is kind of an attempt to generalize this. Next is databases. All those databases have Go APIs, and what you do with your database is you store the data in an actually structured way, so you can quickly access. So it will be a one-time effort of processing it all into the format that is standardized, and then you can quickly access, you can quickly share with other colleagues. Then you have function as a service, so aka serverless. This is where you would serve the model that the data is thinking. So once you have something that comes through and you actually want to ask your data model, what is this? What is the prediction, or what is the outcome? You take your model many times on one of those services. And then it is very much recommended to use a data governance tool. Data governance is a way to describe manipulating data, or making sure that it has the right permissions, and it has the right structure, and it has compliance. What do I mean by that? For example, you want to be GDPR compliant, so you want to have emails in the system, but you don't want that any employee will be able to access them, but only the sysadmin, for example. So setting types of permissions is one way of doing data governance. Let's say you're working with financial information, but you don't have PCI compliance, so it means you're not allowed to store credit card information. So you probably want to make sure you filter from the system with the credit card number, or you only store a hash of it before it even enters your system. This is another example of what is data governance. On top of everything, you should be doing monitoring. Obviously, you want to know that your system is performing well. You can monitor what is the flow of a request through the system. You can monitor how many connections you have to the database, how many predictions were wrong, how many predictions a minute are made, if you have any timeouts, so anything from the performance of the application to the health of it, and so on. And this all together puts one infrastructure that I see as the bare bones, so the very basic infrastructure that would be common to most machine learning applications out there. Let's say we have a bunch of files in different formats, a Parquet, a JSON, a CSV, maybe more. First of all, we do data governance. So let's say we filter out credit card information because we don't want to deal with that, because we're not PCI compliant, because being PCI compliant is a lot of a headache. And I say that after working for a fintech company. Then you store your data in a database and in a data lake, probably. So you store the raw data, but you also structure and format it, and then you store it in a way that's easily accessible. And then you make a second iteration of data governance. This time you decide that most of the fields, for example, the private information, the PII, like the address, the phone number, the email, is not accessible to most developers, but only to the sysadmin. Maybe you make a subset of it in open source so that others can be playing with the data set that you have. And maybe you give different, like a subset of copy of the data that you have to other teams that they can play with that, but they shouldn't be having access to all the fields and so on. And then the data that you have, you do the model training. Once your model is, before we move on, a quick focus on training. The training is this step of the how to do the ML, and there's two parts. There's two ways of doing that. You can do it with a static model or building a dynamic model. Basically, static means you trained the model remotely and then you upload it. And dynamic means that it also gets a feedback loop. There's pros and cons for each. Static model is, of course, easier to build and test because you do this all offline and you only upload when it's done, but it can only know things that you trained it. Also, the update latency is not a few seconds or minutes, but it's actually taking it down, retraining the whole thing, uploading it, and it's hours if you're fast. Dynamic model, on the other hand, has the big advantage that it's able to adjust itself to as long data that is changing, and eventually it will make better predictions. But it's compute intensive, it's latency intensive, and that means you're going to have to put some limitations because you want it to be accurate and fast, and you're going to have to find a trade-off between all of those. And you will need to do more moderation because you don't know what is the finite set of the predictions that it can make, or if it gets stuck because it's complicated query or whatnot. The model training part is one square in our infrastructure, and we said that this is maybe 5% of the data code, the entire code in our system, but people build their entire careers of being data scientists by training models. So please don't take this into any hint from me that this is a simple step or a small step. That's a huge deal. It's incredibly complex. You need good mathematical background. Once you have the model, you put this on your serverless tool of your choice, and you're ready to make your prediction. The prediction is also called inference, and let's zoom on that as well. So this lands us in this stage of how-to machine learning. And you can also separate this into two general types, online and offline. Online makes better predictions as new items come in. And a good example of when you would want to use that is if you have a flower shop. And you know that over the weekend you sell slightly more flowers, during the week you sell slightly less flowers, and your model is kind of telling you that today is Monday, order less, today is Thursday, order more. And then comes February. And then suddenly it sees like February 10, February 11, February 12, there's like a little spike in the sales. And if you have an online model that recognizes that there's a spike, it will tell you, even though it's a Tuesday, buy a lot more flowers. And then you end up being on Valentine's Day not sold out, and you probably made a lot of money on your most profitable day of the year. The cons of it is, as we said, it's compute intensive, it's latency intensive. You will have to find the right trade-off on the performance, and you'll have to put more resources into monitoring it. In comparison, the offline one, the inference cost is practically negligible because it's kind of like you have all the solutions uploaded, and it's like a lookup table. You are likely to use batch quota, and you can do a post-verification of all the predictions, so you make sure that you don't have any funny predictions, because it's a set of all the predictions that is basically a lookup table. The biggest con is that it doesn't handle new information or changes well. And to all of that, we add monitoring, and this is what I would say that the most basic infrastructure for machine learning applications looks like. This is another opinion. So this is a screenshot of the machine learning and artificial intelligence ecosystem in 2019. It has a lot of additional fields that we didn't cover today. And it goes from AI ops to search to visualization to looking all kinds of tools of making the hardware better, all kinds of tools to utilize this. Data integration, data protection, all the places that you upload it to, if it's a GPU, if it's a cloud, if it's a tool to integrate them all. Zooming in on some of the parts of it is also ways to maybe streaming it. Hadoop, we mentioned it also, practically everybody would offer it on-premise and on cloud. Analytics is something that's also very interesting, orchestration, security, mega important, of course. So the alternative to taking a bare bones infrastructure is to take a solution that is off the shelf. And as you might have guessed, TensorFlow offers indeed such a thing. And each square that you see is one tool from TensorFlow Extended, which is an end-to-end platform. And it's a solution that you can take and utilize, and it goes anything from making samples to your data set and making sure that this is statistically making sense and not too biased and so on, through all the transformations that it needs to do, training the model, evaluation, validation, and serving it. And the serving it is done on TensorFlow, so you can do it on the web, which is a traditional way. You can do it on tools that are dedicated to embedded, so your machine learning can predict what day of the week you're going to have the highest load, and it will recommend you to do the laundry at night because electricity is cheaper. You can also serve it from your mobile phone and use the fact that you have a pretty strong machine in your pocket, and it can either make even training on the spot and drain your battery, or just do serving of a model that you have on some server or the cloud and so on, and just use the API in the app. So this goes to say that TensorFlow is available. You can consume and train models of TensorFlow with all kinds of, from huge GPUs to the tiny embedded machines. And now let's look at a concrete example of a company that I will not mention their name, and I will not mention their product, because if I tell you the product, you will immediately recognize. But I will make adaptation of it to spam filter in email. And let's say I'm sending somebody an email, and this is how it looks like. And I'm typing whatever content I want, subject, and then I'm hitting send. And a lot of data comes with it. So there is the sender email, the receiver email, the title, the content, which is visible. And there's also alt information like the header, like the footer. And all this is our input data into the system. This is being stored in Aerospike. The reason I'm giving the example with Aerospike is that I work at Aerospike. I have access to all kinds of interesting use cases from clients, and this is what I'm sharing, actually. So they store it there for the purpose of accessing a lot more information really fast. What do I mean by a lot more information? The input features vector. Input features vector is a way to represent data in a mathematical manner. So we set a lot more criteria and we give them a numerical value. Presence of a recognized header is good. It means it's probably not spam. Let's give it 1. Presence of an official signature, my mail doesn't have that, then it might look funny because many people do have some kind of a template, then let's give it a 0. The structure of the email looks more okay than not, so I evaluate this at 0.7. How often did I use in the email words like prince, special price, how good was my grammatic correctness of the email? And this all kind of puts those numerical values, let's say, and many of them are also pulled out of the database. So for example, I gave the user ID, and for the user ID pulls out a lot, like what's their average email structure value. And then if it's normally somebody who's like not writing enters or spaces a lot, then it's regularly around 0.7, then I'm not suspicious that this is weird. But if it's suddenly like, normally I have perfect emails and it's like 0.9 or 1, and suddenly this email gets 0.1, this would alert a little bit that something looks off about this specific email. So the information that is pulled in the database or from the database is basically the historic information for all the different properties, like the user ID, like the receiver ID, and so on. And then I translated this 6 data points to a vector with 50 data points, for example, or a few hundreds. And this is what I'm giving as an input to the machine learning model that is served on AWS Lambda. The model was developed in-house, and it's served online. And it was written in Python because with tools like TensorFlow, you can use any API, including Go, to serve models. But to develop models, you probably still need Python. That's okay, because you probably also need a lot of mathematical background. The output of the model is whether it's spam or not spam. And the way that it's done is that it's giving a numerical value, so kind of putting into account all the different numerical values from the input feature vector. And based on the current threshold, which is also dynamic, it says, does it pass the threshold or not pass the threshold? Or basically translate to, is this looking okay or not? That was a lot, huh? To recap, and I hope I'm good with time, we covered today what is AI, what is ML, and how to ML. We saw this cool graph or image of some of the things that are considered AI. We talked about TensorFlow, how it's an open source library, but it also has an end-to-end solution, and how it goes on all kinds of serving ways, whether it's a website, whether it's a mobile device, whether it's an embedded tiny piece of electronics. We discussed why is it called TensorFlow, so your data is represented as a tensor and it flows through the graph. And we discussed the different types of training and inference, how it can be online and how it can be offline, pros and cons of each. We discussed what is my personal opinion of a bare bones architecture components for any machine learning one, something like this. We discussed that there's a little more to it than the bare bones. And we looked at a concrete architecture example that is actually being used in production in a massive scale. And it looks like this. And some interesting fun facts is that the code of machine learning model is actually about 5% or less of the entire machine learning system. The input data is a tricky part of a machine learning system, and you do need to do data governance. And the bare bones flow would include processing the data, storing it, training the model, serving predictions, and monitoring everything. Thank you very much. And if you learned or found something interesting, please tweet and share.